This is the third video in the topic on how does a hot air balloon work. In this video we're going to be looking at Archimedes' Principle and the buoyancy force. So the question is, Archimedes read the volume of a bucket of water to be 10.222 litres. He then placed the crown into the bucket and noticed that the water rose to a volume of 10.273 litres. The crown had a mass of 894 grams. Now, is the crown made of pure gold? And if not, what fraction is silver and what fraction is gold? And we're told that the density of gold is 19.30 grams per centimeter cubed, and the density of silver is 10.49 grams per centimeter cubed. So let's start by working out the density of this crown. That will tell us if it's made of pure gold or not. So to work out the density, we're going to have to use the density is equal to the mass over the volume. So we'll need to start by working out the volume of the crown. So the volume is equal to the final volume of the bucket of water minus the initial volume of the bucket of water. So that's 10.273 minus 10.222. And so that is equal to 0.051 litres. Now these densities are in centimetres cubed, which is millilitres. So to convert this into millilitres, we need to times it by 1,000. So the volume of the crown is equal to 51 centimeters cubed. Or we could write milliliters here if we want. Those are the same units. Okay, so we've now got the volume, so now we can get the density. The density is equal to 894 grams over 51 centimeters cubed, and so this gives us a density of 17.5 grams per centimeter cubed. So you can see this is less than the density of gold, so this tells us the crown is not made of pure gold. Okay, now we're going to need to clear some space to work out what fraction of it is silver and what fraction of it is gold. Okay, so we've got that the density of the crown is equal to 17.5 grams per centimeter cubed. The density of gold is equal to 19.30 grams per centimeter cubed, and the density of silver is equal to 10.49 grams per centimeter cubed. The other thing we knew was that the volume of the crown was equal to 51 centimeters cubed. Now we know that the crown is made up of the volume of gold plus the volume of silver, which went into making it. So we can say that the volume of gold in the crown is equal to 51 centimeters cubed minus the volume of silver. So that's one equation we've got. Let's call that equation 1. Now the other thing we know is the mass of the crown. So we know that the mass of the crown is equal to the mass of the gold in the crown plus the mass of the silver in the crown. So the mass of gold in the crown is the density of gold times the volume of gold, and the mass of silver is the density of silver times the volume of silver. So we've got that the mass of the crown is 894 grams, the density of gold is 9.30 times the volume of gold, and the density of silver is 10.49 times the volume of silver. So what we've got now is two equations that we're going to have to solve simultaneously. So this is getting a little bit complicated, but all we need to do is replace this volume of gold here with this equation here. So we've got 894 is equal to 19.30 times the volume of gold, which is 51 minus the volume of silver, plus 10.49 times the volume of silver. And so we've got 894 is equal to 19.3 times 51, which is 984.3 minus 19.30 times the volume of silver, plus 10.49 times the volume of silver. Now we're going to need to do some algebra to rearrange this. We'll move the two terms with the volume of silver over to the left-hand side and move all the terms with just numbers over to the right-hand side. So we've got 19.30 times the volume of silver minus 10.49 times the volume of silver is equal to 984.3 minus 894. And so we can take the volume of silver out as a common factor here. And what we end up with on this side is 8.81 times the volume of silver is equal to 90.3. And so the volume of silver is 19.3 divided by 8.81, which is equal to 10.2 centimeters cubed. And the volume of gold from this equation here is just 51 minus the 10.2, and so that gives us 40.8 centimeters cubed. So there's 4 times as much gold as silver, so this combined tells us that it's 1/5 is silver and 4/5 is gold. And so if these were the values that Archimedes really measured, then the goldsmith had cheated King Hero. Let's measure the density of the green bottle and the red bottle now. To measure the density, we need to work out the mass and also the volume of these two bottles. So using Archimedes' method, we can work out the volume of water displaced by the bottle when we submerge it. So at the moment, this beaker is saying that there are 3,000 millilitres of water in here. Let's now submerge this red bottle. It's now saying that there are 3,600 millilitres of water in the beaker. So this bottle has a volume of 600 millilitres. Now to get its density, we also need to measure its mass. So let's take the handle off and we can weigh it. It has a mass of 1.2 kilograms. So to get the density, we do the mass, the 1.2, divided by the volume, which was 600 millilitres. And so this tells us that the density is equal to, we get 2 kilograms per litre. So that's quite a lot more dense than water. Let's now check this much lighter green bottle. When we put this one into the water, the volume is displaced up to 3,600 millilitres. So this has a volume of 600 millilitres. Let's now check its mass. The mass of this one is 30 grams. So 30 grams divided by 600 millilitres. So 30 grams divided by 0.6 litres gives us 50 grams per litre or 0.05 kilograms per litre. So this one is much less dense than this one. Now one other interesting thing to note is that when we submerge this, the volume increases by 600 millilitres, but the mass on the scale also goes up by 600 grams. Now this is actually because of a reaction force. This water is providing a buoyancy force to the bottle. So the buoyancy force provided on the bottle is the weight of the bottle times the volume. So the buoyancy force it provides to the bottle is equal to rho Vg, and so that's proportional to the volume. Now to get that buoyancy force, there's an associated force of the bottle pushing downwards on the scale. And so the scale actually reads an extra 600 grams, which is equal to the mass of that water which is displaced by the bottle. With the red bottle, we get the same reading on the scales. It's also changed by approximately 600 grams because we've got the same mass of water displaced. It doesn't matter about the different densities. If I let go of this handle, the reading goes up a lot because we've added the extra weight force from the red bottle. Archimedes' principle is that the upwards buoyancy force on an object is equal to the weight of the fluid that the object displaces. So have you ever wondered why when you get into a swimming pool it feels like you are floating, and then if you get into seawater it feels like you're floating even more? Well, this is because your body has volume. When you get into the water, you're displacing a certain volume of water. And so there's a buoyancy force on your body. And that buoyancy force is equal to the weight of the water that your body displaces. Now you may have heard about the Dead Sea, which is near Jordan. The Dead Sea has an especially high density. If you have a metre cubed of water from the Dead Sea, that's got a density of 1,240, well, that would have a mass of 1,240 kilograms. Whereas fresh water, if you have 1 metre cubed, weighs 1,000 kilograms.
So in the Dead Sea, people float even more because the density of the Dead Sea is very close to the density of the human body, and so you float without even trying in the Dead Sea. So let's go back to considering hot air balloons. Hot air balloons have a buoyancy force because they displace some of the air. As we'll see with the ideal gas law, there is air inside a hot air balloon, but the air inside the hot air balloon is less dense than the surrounding air. So another example of this is actually with helium balloons.
So the question is, a balloon has a volume of 3.50 litres. The mass of the balloon and string is 2.0 grams. It is filled with helium with a density of 0.1786 grams per litre. If air has a density of 1.22 grams per litre, what minimum mass must be tied to the balloon to stop it from floating away? Okay, so let's consider what's going on. Here we've got our balloon. Now the balloon's got a buoyancy force upwards, and this buoyancy force is equal to the weight of air displaced. That's Archimedes Principle. And downwards we tie on a mass and it's got a weight force. Now to stop the balloon flying away, this buoyancy force and this weight force need to be equal to each other. If the weight force is larger than the buoyancy force, then the balloon will not fly away, but the limiting case with the minimum mass is when the weight force is equal to the buoyancy force. So let's start by working out the weight force. So there's three things contributing to the weight force, three masses. We've got the mass of the balloon plus the string, which we're told is 2.0 grams. We've then got the mass, which we tie onto it, which we need to find. So let's call that M. And then finally, we've got helium inside the balloon, and so we've got the mass of that helium as well. So that's the density of helium times the volume of the balloon. And then to make it into a weight force, instead of just a mass, we need to multiply that by G. So the density of helium is 0.1786. The volume of the balloon is 3.50 litres, and so we have the mass of the helium inside the balloon is equal to 0.625 grams. And so we've got 2.625 grams plus the mass in grams times G will be our force in millinewtons. Okay, so now what we need to do is work out this buoyancy force. So the buoyancy force is just equal to the weight of the air displaced. So that is equal to the mass of the air times G, and the mass of air is the density of air times the volume of the air, which is displaced, times G. And so this is equal to 1.22 times 3.5 times G. And so this is equal to 4.27 G. Now what we've said is that our buoyancy force must be equal to our weight force. So we can set this one here equal to this one here. So we have 2.625 plus M times G is equal to 4.27 G. These G's cancel out. Now all these masses are in grams, and so our final mass is 4.27 minus 2.625. So this gives us 1.65 grams is the mass that must be tied to the end of the balloon there.
Now the same principle applies to boats as well. Boats float because they displace a certain weight of water. The weight of water that a boat displaces is equal to the weight of the boat. So if you have an oil tanker which is full of oil, it'll float very low in the water. If you have an empty oil tanker, on the other hand, it'll float much higher and will displace a lot less water. Let's have a look at a demonstration now involving boats. Here's a problem for you to try. This is called the fisherman's puzzle. Imagine that we have a lake like this beaker of water, and there's fishermen with all their anchors and everything in a boat on the lake. There we go. Now we'll mark the height of the lake with a pen here so you can see what the water level is. Now the fishermen are having a bit of a debate on the boat. Some of them are saying, well, if we jump out of the boat, we'll be taking up the same volume of water as we would in the boat, so the volume of the water won't change. And others are going, oh no, hang on. If we jump out, we're more dense than the surrounding water, so we'll displace less volume and the volume of the lake will sink. So have a think for a minute. What is going to happen if these fishermen, which are more dense than the surrounding water, jump out of the boat and into the lake? Okay, hopefully you've now had to think about what will happen. Let's do the experiment and see what happens to the volume of the lake. Okay, the volume of the lake has dropped significantly. Now that's because these objects are more dense. And so when they sink to the bottom, they displace less water than their weight force. So in this case, their weight force, the downwards force, is larger than the buoyancy force, the upwards force. So now they displace less water. When they were in the boat, they caused the boat to sink. so that the volume displaced by the boat had the same weight as the weight of all the objects together inside the boat. What I have here is a fish tank filled with water and an ice block that I've made, which is just water with a little bit of blue food dye added to it so that you can easily see the ice. Now, as we discussed in the kettle topic, water is a very special liquid because as it freezes, it actually expands. So as it expands, it becomes less dense. And so because the ice is less dense than the water, we would expect the ice to float on the water. Let's do a calculation now to work out what percentage of an iceberg we would expect to be underwater.
Okay, so what we're doing in this case is we've got an ice block, and let's say that it's got some volume V of ice, and we're floating it in fresh water. So we know that the density of the ice is equal to 0.9167 grams per centimetre cubed, and that the density of the water is equal to 1.000 grams per centimetre cubed. Now, if this was salt water, it would be slightly more dense, but in this demonstration it was fresh water, so we're going to be using fresh water in our calculation. Now, we know that the net force acting on our ice block is 0 because the ice block is not moving. So we've got a buoyancy force pushing the iceberg up and a weight force pushing the iceberg down, and these two forces must balance each other or the iceberg would accelerate, and it's not accelerating, it's remaining stationary. Okay, so the buoyancy force is equal to the weight of the water displaced. So we can call this volume here, let's call that V water. That's the volume of the water displaced. So the buoyancy force is equal to the mass of the water displaced times G, which is equal to the volume of the water displaced times the density of the water times G. And the weight force for the ice block is just equal to the mass of the ice times G, which is once again just equal to the volume of the ice block times the density of the ice times G. So now what we want to equate is this part here and this part here. So we've got that the volume of the water times the density of the water times G is equal to the volume of the ice times the density of the ice times G. And these G's cancel out, they're both just 9.8. And so what we wanted to work out was what fraction of the iceberg is underwater. So the volume found underwater is equal to the volume of the ice block times the density of the ice block divided by the density of water. So the density of the ice block is 0.9167 divided by the density of water, which is 1. So this is 0.9167 times the volume of the ice block is the percentage that is underwater. So this tells us, to get it into a percentage, we times it by 100. So 0.9167 times 100 tells us that approximately 92% is underwater. Now with salt water, it's going to be a slightly lower percentage underwater because salt water is more dense than fresh water.
So now that we've calculated how much of an iceberg will be underwater, let's have a look at what happens when we put this ice block into the water in the fish tank. So you can see, as we expected, the majority of the ice block is underwater and just a small fraction of it is on top of the water. Let's do an experiment similar to what Archimedes did now. What we have here is a lump of metal. This is aluminium. Here I've got what's called a Newton spring balance. This will weigh the mass of this aluminium metal here. So we can lift it up and you can see on those scales that this has a mass of approximately 900 grams. Now what we're going to do is we're going to submerge this mass in the water. Now, according to Archimedes' principle, there should be a buoyancy force pushing up on this metal equal to the weight of the water displaced by the metal, which should mean that the scales read a lower number when this mass is submerged. So let's submerge it now. Now you can see on these scales, now that it's submerged, the scales are reading approximately 600 grams, suggesting that 300 grams or 300 millilitres of water has been displaced. So the water which has been displaced by this metal is gradually draining out of this beaker. So as soon as that's finished, we can read off the mass of the water in this beaker, which will be proportional to its volume. So let's read off that mass now. So the mass scales here, and the volume is saying 300. So 300 grams, 300 millilitres of water, which is the difference in the force recorded on this Newton spring balance here. So in this video, we've seen that we can calculate the density of an object using the formula density is equal to the mass over the volume. We've seen that, as suggested by Archimedes, if we want to work out the volume of an object, we can put it into water and see how much water it displaces. The volume of water it displaces is equal to the volume of the object itself. Now, Archimedes' principle says that the buoyancy force, the upwards force that an object experiences, is equal to the weight of the fluid that it displaces. So with a hot air balloon, it actually experiences a buoyancy force because the air inside the hot air balloon is less dense than the air surrounding the hot air balloon. So in the next video, what we're going to be looking at is how the air inside that balloon becomes less dense. So we'll be looking at the ideal gas law, which allows us to calculate the density of the air inside the balloon and hence to calculate the size of the buoyancy force on the hot air balloon.
Special thanks to Sebastian Frick for filming this. Also thanks to these people who provided the images of the oil tankers that were used.